I've got a differential equation up here on the board, and again, we're going to solve it by approximating with series. So we're supposed to approximate the solution using a Maclaurin series, and we're going to find the fourth Maclaurin polynomial. Remember, we're working with the series, so I'm not claiming that the fourth Maclaurin polynomial is a solution. I'm claiming that the fourth Maclaurin polynomial consists of the first few terms of a series, which is a solution to the differential equation. Okay, so let's see. I'm going to basically be supposing that y of t is the sum as n goes from 0 to infinity of a sub n t to the n. So what I'm going to do here is I'm going to just write out what I have on the left-hand side of my equation, which is y plus a y prime. Okay, order doesn't matter. I'm going to add those two together. Okay, so y would be a naught plus a1t plus a2t squared plus a3t cubed plus a4t to the fourth plus plus plus. The series goes on. Okay. Y prime, well, if I take the derivative of a constant, that's just 0, so that goes away. The derivative of a1t is a1. Now I'm going to line that up with the constant that I have, because these two together are going to be the constant that I have on the left-hand side of my equation. Now, when I take the derivative of the next term, I'm going to get plus 2a2t, and I'll line that up with the other t's that I have. These two pieces together give me the linear term on the left side of my equation. Continuing on, we get 3a3t squared plus 4a4t cubed, plus, even though I didn't write the next term here, I can see I'm going to get 5a4 t to the fourth plus dot dot dot, and it goes on and on. Okay, excellent. Now, on the right-hand side, I'm getting e to the negative 3t. So let's remind ourselves of what the series is for that. So e to the t is the infinite sum of the nth power over the nth factorial. Okay. E to the negative 3t, well, that's just a function composition. That's what I get if I plug in negative 3t for t. So I'm just going to plug in negative 3t for t. So that's going to be the sum as n goes from 0 to infinity, negative 3t to the n over n factorial. Now, I do want to simplify just a little bit, because I want to have powers of t. Right now I've got powers of negative 3t. I usually actually will break that up into a three-part power. I'm going to say that's negative 1 to the n, 3 to the n, t to the n. Not absolutely necessary to do that, but the negative 1 to the n is really nice, because it just gives me alternating signs with the terms. So I can see we're going to go positive, negative, et cetera, et cetera. Okay. And then, of course, over n factorial. Okay. Now, I should point out, in this problem, I'm just doing essentially what you're going to be asked to do in the homework, which is to find the series up to a certain degree, to find, in this case, the fourth Maclaurin polynomial. For that reason, I'm not trying to describe all of the coefficients. I don't really care about noticing a pattern and being able to describe that pattern that continues infinitely. I just want to know 5 numbers, the constant term, the coefficient in front of t, t squared, t cubed, and t to the fourth. So as I plug in my values for n, I'm going to simplify things fully. If I were looking for the entire series, and you're generally not asked to do that in the homework, so I'm going to try to keep my examples like this, where we're looking for a specific polynomial. Okay, but if I were looking for the whole pattern, I'd probably keep it this way, because when I write it this way, I can see the pattern for generating those terms. Okay, so let's see. When n is 0, anything to the 0 is just 1. 0 factorial is 1, so my constant term is 1. My next term is going to be negative, because like I said, we've got alternating signs, so negative 1 to the first will make that negative. My coefficient is going to be 3 to the first over 1 factorial, so that's just 3 over 1, so I get 3t. Plus, the next term is positive. 3 squared over 2 factorial is just 2 times 1. So that's going to be 9 over 2t squared minus, next term is negative, okay, Now here, I'm getting 3 cubed, which is 27, over 3 factorial, which is 3 times 2 times 1. I can cancel a 3. So I'm going to get minus 9 halves t cubed. Okay. When I'm finding the fourth polynomial, I want to simplify things as much as possible. If I were looking for a pattern, I probably wouldn't want to cancel those 3's, because it's a lot easier to see the pattern when I see that that was 3 cubed on top and 3 factorial on the bottom. Okay, and then let's see, when n is 4, it's going to be positive. We're going to have 3 to the 4th, which is 81, over 4 factorial. But that's 4 times 3 times 2 times 1. I can cancel a factor of 3. So that's going to become 27 over 8 t to the 4th. Plus, well, actually the next one will be minus, and then dot, dot, dot. It continues on and on. Okay, so hopefully I've got enough information now to solve for things. Now, I did not in this problem give you an initial value, okay? So I want to remember that A naught is always just the initial condition. I'm going to be writing everything now in terms of an arbitrary initial condition that we'll just call A naught. But notice, if you were to plug in 0 for t, all of these powers of t would just die off. I'd be getting exactly just A naught. So A naught is always the constant term of my, or the initial condition of my function. Okay, excellent. So, let's see, if I look at the constant term here, I get that A naught plus A1 is equal to 1. Well, that allows me to solve for A1. A1 is going to be 1 minus A naught. Okay. So I can describe it in terms of that initial condition. Now, if I had a specific number for this, I'd plug in that specific number. Here, I'm solving the family of differential equations, not just a single initial value problem. Okay, now if I look at the t's, okay, I'm going to have A1 plus 2A2 is equal to negative 3. Okay. I want to plug in what I know for A1. Okay. So I think what I'm going to do is I'm going to subtract over A1. So 2A2 is equal to negative 3 minus A1. But for A1, I'm going to write 1 minus A naught. So I'm going to get negative 3 minus 1 plus A naught. So that's going to be negative 4 plus A naught. So A2, I'm going to get by just dividing by 2. We'll have negative 2 plus A naught divided by 2. Okay, excellent. Now I got that by looking at my t's. Notice that's A2, but I didn't get that by looking at the t squareds, because that involved an A3. Okay, I got that the first time A2 showed up was actually in the t's. So now I'm going to look at the t squareds, and I'm going to say here, now A2 plus 3A3 has to equal 9 halves. So 3A3 is going to equal 9 halves minus A2. But if I subtract A2 over, that's going to mean plus 2 minus A naught over 2. So 3A3, that's 9 halves plus 4 halves. That's going to be 13 halves minus A naught over 2. A3 is going to be 13 sixths minus, it's an A naught, isn't it? Minus A naught over 6. Okay, excellent. And I just need to find A4. So this is kind of nice. I'm not actually going to have to go all the way to the t to the fourths, because A4 first shows up in the t cubes. So I'm going to just clear myself some space here. But I can see, looking at the t cubes, on the left I have A3 plus 4A4, and that's got to equal my 9 halves. So 4A4 is going to be 9 halves minus A3. But when I subtract a3, I'm going to plug in what I have. So that's going to become minus 13/6 plus a naught over 6. Okay. So let's see, 9/2 would be 27/6 minus 13/6. That would be 14/6, which I can reduce. Let's go ahead and reduce. So 4a4 is going to be 7/3 plus a naught over 6. a4, I'm going to just divide through by 4. It's going to be 7/12 plus a naught over 24. All right, so I've got all of my coefficients. Now, I've pretty much done all of the work I need to do, but let's not forget to actually write the answer. We wanted P4 of t, which is a naught, plus we're going to have some t's, plus some t squareds, plus, I might run out of space, so I'm going to continue down here, some t cubed, plus some t to the fourth, and now I just have to fill in those coefficients. So the coefficient for t was a1, which we said was 1 minus a naught. The coefficient for t squared is a2, that's negative 2 plus a naught over 2. Coefficient for t cubed, that was my a3, that was 13/6 minus a naught over 6. And the coefficient for t to the fourth is what we just found here, 7/12 plus a naught to the 24th. A naught over 24, I'm sorry, not to the 24th. Okay, so I'm able to actually find my fourth Maclaurin polynomial. Now, I will confess, this example was a linear differential equation. We've got way better techniques for actually finding the solution rather than just approximating it. So some of the problems, in fact, many of the problems that you're doing in the homework are actually just going to be sort of practice to get familiar with this concept. We've got other techniques that work because we're working with relatively nice differential equations. But this technique of approximating things with a series does work fairly nicely for a number of differential equations, and we're just sort of getting our feet wet, and none of them are too complicated in the homework that you're going to have for this particular section. I will point out, though, one problem that shows where this technique can actually be quite useful is problem number 9. In problem number 9, we're working with tangent of t. So this is 9 in the homework. I'm going to leave it for you to do it, but I want to sort of talk about its significance. If y of t is tangent of t, then I know that y prime of t is secant squared t, and I know that that's 1 plus tangent squared of t. So I know that this is a solution to y prime equals 1 plus y squared. Okay. Now, I could solve that by separation of variables and stuff like that. But if I solve by series, I'm going to be getting, assuming I plug in the correct initial conditions, but if I solve by series, I can find a Maclaurin series for tangent, which is otherwise a royal pain to find, because the definition of Maclaurin series has those coefficients being the nth derivative divided by n factorial. But the first derivative is secant squared. The second derivative is 2 times secant times tangent. The derivatives just get more and more complicated, and I start having to use product rule again and again and again. So finding a whole bunch of derivatives to find the Maclaurin series by the definition is incredibly tedious. I can use the fact that tangent is sine divided by cosine and try to work with dividing the series, and you just basically have this infinite division problem and you just do the first part of it. Okay, but that's kind of tedious. Now you are going to have something similar here because you are going to have your y squared. Okay, so you're going to be essentially squaring your Taylor series. Okay, but when you do that, you're not going to actually multiply every term by every term. You're just going to multiply out the first few terms because only the first few terms will give you the smaller powers. Once you're multiplying by bigger and bigger powers, anything I multiply by t to the 6th is going to give me something of degree 6 or more. So if I only care about the fourth degree polynomial, I don't care about those terms and what I get when I multiply things out. So it's a little bit tedious, but it might be a more efficient way of finding the Maclaurin series for tangent than any other technique that we have at this particular point.